All right, why don't we get started with our first speaker?
Hello, can you hear me well? Oh, maybe. Can you hear me well? Yes, then I will start. Yes, hi, I am Eun-jin Shin. I'm a PhD student working with Eun-Kim at Seoul National University. Actually, I said I'm a PhD student, but this month is the final month for my PhD course, and I will move to Cambridge on this October. So yeah, today I will talk about the dark matter deficient galaxy produced by high velocity galaxy collision, and I studied this in numerical simulation. This work is done with Julian Lee at UT Austin and my advisor Jung Kim. So yeah, you might know about the DF2 and DF4. These are ultra-diffuse galaxy with stellar mass of 2 times 10 to the 8 solar mass. They are found nearby giant elliptical galaxy and this 1052, and reported by Van de Kun group. They reported about the dynamical mass of DF2, and this dynamical mass is similar to stellar mass, which means they are dark matter deficient. And they also, DF2 and DF4 share very unusual property. They have unusually bright population of globular cluster inside the system. So many researchers got interested in this system, and many interesting scenarios were suggested. And what we focused on is the black cluster idea. As we know, the black cluster is the event that occurred by the different collision nature of dark matter and gas. And if this black cluster kind event happen in galaxy scale, then this can produce dark matter deficient galaxy. So if the typical galaxy collide with high velocity, then the dark matter just pass through each other since they don't interact electromagnetically. However, gas interact electromagnetically, and it can suffer the pressure, and they can remain in the collision spot. So if this gas can be cooled and produce stars and become galaxy, then this can be a dark matter deficient galaxy. So we tested this scenario in numerical simulation. For the reproducibility, we tested both mesh-based code ENJO and particle-based code gadget, and I only brought the ENJO result since they are almost same. So we see that 2 progenitors are colliding, and we can see the gas, large amount of gas is remaining in the collision spot, and they produce the stars, and dark matter are just pass through each other, so these are the dark matter deficient. And we could see that the stellar mass is around 10 to the 8 solar mass, which is similar to the observed DF2 and DF4. And we can see that multiple number of dark matter deficient galaxies are formed along this line of connecting these 2 progenitors. So single collision may create the multiple number of dark matter deficient galaxies. So also we tested the enclosed mass profile of the most massive dark matter deficient galaxy, and we can see that the gas and stars are the baryons are the dominated in this structure, and we can see that they are dark matter deficient. And right shows the star formation history, and we can see that star formation rate boosts when the galaxy are in pericentric approach, which means the star formation is boosted by the shock in the collision. And the produced mass is around 2 times 10 to the 8, which is similar to the observed DF2 and DF4. So yeah, then maybe we can ask that what kind of this collision event can produce this kind of galaxy? And we tested galaxy collision parameter. And I tested the relative collision velocity, pericentric distance, and relative angle between 2 progenitors, and initial mass ratio and initial gas fraction. And the red color presents the parameter that can produce the dark matter deficient galaxy. Maybe I cannot explain the detail, so maybe we can now ask that how often does this kind of event occur in our universe? So to answer this question, we investigate the illustrated TNG universe, and based on the previous parameter study, we could estimate the number of collision events in this universe, and we found 250 galaxy collision can happen, and in this 100 megaparsec cube volume, and this number is around 8 cases. inside the volume connecting the Earth to and this 1052. So maybe we can find the 8 cases or around 8 cases based on this study. And now we can ask that what is the inner structure of the dark matter deficient galaxy, which is induced by the collision event. And to answer this question, we implemented the 1.25 parsec resolution simulation, and this result almost reproduced the previous result, and we could see the inner structure of the DMDG, and also we can find the global clusters. So this shows the enclosed mass profile of the DMDG in 1.25 parsec resolution, and we can see that they are still baryon dominated and dark matter deficient, and we could see the rotation curve of the most massive dark matter deficient galaxy, and the dots shows the star cluster location, and these 5 are the most massive star cluster inside the DMDG. And the right shows the velocity projection of the DMDG, and the circle represents the star cluster, and the size is the mass of each star clusters. And we could find that 42 star clusters are created, and they are bound in the dark matter deficient galaxy. And what we found is that extremely massive star clusters are created in DMDG, because in this scenario, the highly dense gas can be made by the shock. So it explains the unusually bright population of global cluster in DF2 and DF4. And this was very exciting news for our group. So last year, so I will explain this. So this result shows the 22 result of 2020 of our result, and we could see that along the progenitors, we can see the multiple number of dark matter deficient galaxies are formed, and almost similar this feature are found in the real sky. This is reported by Van Dokken group, and large diffuse galaxies are around 11 large diffuse galaxies are coincidentally located along this DF2 and DF4 axis, and this shows the system nearby, and this 1052, and color shows the size of the systems, and we can see the red color are reside in the line in DF2, DF4 axis, and they suggest that the single web dwarf collision might be the origin of this subset of the 11 objects, and these are also consistent with the age measurement of just global clusters and stellar bodies, and the color is almost same in the DF2 and DF4 system. So yeah, the relative velocity of DF2 and DF4 is 300 km per second, which is similar to our simulated parameter. And based on the line of sight velocity and the location information of DF2 and DF4, we can trace back in time, and we can obtain the possible possible collision parameter to produce this current day DF2 and DF4. So we tested that in our simulation. This is done with Jun Lee at Houston, and so we tested we found possible initial condition which can produce the current day DF2 and DF4, and we predicted 3D position, velocity, and metallicity, stellar age, and size of trailed galaxy in NC 1052. And we brought 3 examples of possible initial condition, and this shows the around 8 gigayear evolution of this system. And the projected information of position and velocity of this system follows the linear relation. However, I will talk about this in the next slide. The location and velocity of DMDG can deviate from this linear relationship, and we can answer some question about the other researchers, like in this experiment, like Ogiaeder. So, and this 1052 can strip the global cluster in DF2 and DF4, but in our test, to reproduce this DF2 and DF4 current observation. This is hardly in our scenario because they are not inside in the real radius during the 8 gigayear, so it cannot be happen. And when we see this one of example, we can see that the galaxies are deviated from the linear relationship since the end of 1052, and also the velocity is far from velocity of the system in the produced galaxies are deviated from the prediction. So the deviation can be around 250 kilometers per second. So this also answered the Gannon's error question. Like recent observation of DF2 is around 128 kilometers per second, and since our result make more than 250 kilometers, so DF5 also can survive through this criteria. And yeah, the location and velocity of individual DMDGs can deviate from this linear relationship. So I will show this summary slide and ending my talk. Thank you very much.
So, yeah, I wonder, what kind of instability that causes them to fragment into a string of objects, or is it multiple interactions? Maybe you mentioned it.
Yes.
Fangzhou asking, yeah.
So most of the global cluster are formed in the state in the percentile approach, and in this simulation, the star formation is boosted by the shock, and also tidally compressed first. And in this, so the gas cylinder is created by the tidal force, and inside this, the gravitational instability happen and from stars.
Hi, Dhruvo Datta Chaudhary. So you showed this figure where you had all the dark matter deficient galaxies, and there was something about a dashed line and a solid line, where the solid line was DMDGs from simulations, and dashed line was DMDGs from orbit integration.
I mean this
yeah,
figure.
I think if you go to the next slide. Yeah, so you have the green solid line, which is other DMDGs from simulation, and then you have the dashed solid line, which is other DMDGs from orbit integration. So I didn't understand this. So you have are these self-consistent simulations with like gas and dark matter and everything, and then why do you have the orbit integration thing?
Yeah,
and
actually, yeah.
So that is one question. The other question that I had was, are you able to reproduce the mass distribution of, like, from observations? I think we know that DF2 and DF4 are more massive than the low mass objects that lie in between them. So are you able to reproduce that in your self-consistent like collision simulations, like the mass distribution of the DMDGs along this line?
Thank you for your question. Actually, this experiment is so we done the hydrodynamic simulation by 2 gigayear, and then based on the result of 2 gigayear result, we then orbit integration, and we obtained the 8 gigayear or 6 gigayear result. So this is not from the hydrodynamic, but just orbit calculation of the previous result. And the second question, this shows the mass of the produced DMDG, and we could see that actually this doesn't show the DF2 and DF4, but we could see the DF2 and DF4 mass is around 2 times 10 to the 8 solar mass, and they are more massive than the inside DMDGs. And this depends on this highly depends on the state of the progenitors. And for this test, the gas more large amount of the gas can reside in the edge side. So yeah, it can produce the massive DMDGs.
One last very short question from David while Fangzhou sits up.
Thank you for a nice talk. David Koo, Santa Cruz. I was curious about the effects of feedback, supernova feedback. Usually dwarfs have, eta factors are very high. Do you use anything unusual in the IMF or something to prevent the expulsion of the gas from these systems? Or nothing special and they survive the starburst?
Actually, we didn't test the different IMF tests, but we tested the feedback test. We increased the feedback and see how the star formation rate change. And actually, for the higher feedback, it suppressed the star formation rate. So yeah. So it depends on the feedback, but yes. So I can answer that.
Right. All right. Thank you for having me here.